Today, our 4.2, we're kind of cycling back to that. We're going to wrap up our last theorem of the semester. It's not our last theorem overall. We'll have some more second semester, but it's our last theorem of the semester. The slide you have in your deck after that, you've already downloaded it, so I couldn't change what you already have downloaded, but we're not going to use, I think, does it say slide, what does it say at the bottom? Does it say slide 10 at the bottom? Yeah, we're not going to use that one. That shouldn't be there. But if you can insert a blank one, that would be helpful. I can't in this particular screencasting app, but just on that blank one, I want to talk quickly about the two theorems that we've had before. I don't even need you to tell me what it is, but do you remember any of the names of the theorems that we've done? Okay, intermediate value theorem. Good, the IVT. So on that blank one, I want you to jot down, we're going to talk through some of the things we remember about the IVT. Okay. The IVT had a requirement. What did it require about the function? Okay, I heard a couple different things. With confidence. If somebody... no, it doesn't have, that's for inverse functions, has to pass the VLT and the HLT. Okay, anybody else? Has to be, it does not have to be differentiable. We're coming to that. It only had to be continuous. So the IVT, there has to be continuous, all right? What does the word intermediate lend us to kind of associate that with? In the middle, okay? Intermediate in the middle. So what that says is if you have a continuous function, and if you have one value that's on one side of the x-axis, and one value that's on the other side of the x-axis, then there will be a 0 in the middle of those, in the intermediate section, that you can always prove the existence of a 0. So I want you to have written down what is required for the IVT. The IVT requires continuity. It requires an endpoints, and the endpoints have to be on opposite sides of the x-axis. It doesn't matter to me if it goes low to high or high to low, but it has to be on opposite sides. The endpoints have to be continuous and on opposite sides of the x-axis. That guarantees a 0 or a solution there. Okay, that was one of our theorems so far. All right, you remember the acronym of the other one? It was actually in this chapter. It's another vowel, so go through the vowels in your mind. It's the EVT, okay? Remember what E stood for? Nope, it stands for extreme. Okay, we've been talking about extreme. So this is the extreme value theorem. The extreme value theorem also required continuity. It also required it requires endpoints, a closed interval. So if you have endpoints of a closed interval of a continuous function, you are guaranteed extreme values. That means you are guaranteed that a maximum will exist and a minimum will exist. You're guaranteed the existence of them. Doesn't tell you what they are, but it tells you that they exist. All right, so those are the two theorems we've done so far, EVT and IVT. Okay, IVT to prove that a 0 exists. EVT to prove that extreme values exist. All right, we are going to move on to our last one for this semester, which is the MVT. Okay, so now you should be on slide 11. The MVT stands for the mean value theorem. Mean does not have the connotation of being like nasty or a bully or something like that. What's the other meaning of that word? Average. So you could think of it as the average value theorem as well. I want you to just, okay, anything you understand from what you read. Nathan? What does that mean? Okay, so he honed in on instantaneous rate of change, which is great. That means derivative. Okay.
It's just saying that if there are 2 points and the entire graph is continuous, then there's at least 1 point that's equal to the average rate of change.
You're almost exactly there. Yeah, let's talk about what's required first, though. Okay, what else do you understand? Yeah, go ahead, Josh.
Oh, that,
Yes.
it requires it to be both continuous and different.
Okay, so this is a big one, that it requires both continuity and differentiability this time. This is the first time that it has to not only be continuous, and when it says it has a closed interval, what does that mean it has? Okay, so it's continuous, it has endpoints, and we have that it's required to be differentiable, which means what doesn't it have? Doesn't have corners or cusps. So it does have to be continuous, it does have to have endpoints, it cannot have corners or cusps or vertical tangents or any asymptotes or anything like that. So those are the requirements. All right, so Micah, yeah, we're getting now to what does it actually mean? So we understand that instantaneous rate of change means derivative. What other kind of rate of change does it telling us about? The mean rate of change, which means the average rate of change, or AKA average rate of change. And what is it guaranteeing about those two things? They are equal at some point, somewhere. So they are equal. Yeah. Doesn't mean they intersect. No, it just means they are equal. All right, so let's write this mathematically. The derivative equals the average rate of change. How do we write that? How do we write the derivative? Let's use primes. Okay, f prime of x. Okay, then what would come next? Equals, and then what's the average rate of change? Okay, yeah, y2, what? Let's use function notation. What is the average? I'll give you a hint. F of b minus f of a over b minus a. Okay? So that's the meaning. This is the mean value theorem. If the function demonstrates continuity, if it indicates endpoints, and if it's differentiable, then we are guaranteed that this is an equation that has a solution somewhere in there, that these two things, the two kinds of rates of change, must be equal. So now I want to talk about what that looks like. The instantaneous rate of change, or the derivative, what does that look like? What does the derivative look like? Yep, what kind of slope? Just tangent, right? Tangent slope. Right, what does average rate of change look like? That's also slope, but what kind of slope? Not tangent, but secant slope, which means it connects the endpoints. All right, so here's a drawing. This is a secant slope. Okay, my endpoints are A and B right here, going from A to B. This is what's called a secant slope. Because this is continuous, I have endpoints, and it's differentiable, that means I am guaranteed a tangent slope that is equal. And when two slopes of any kind are equal, what do they look like? They're parallel. When two slopes are equal to each other, which means I am guaranteed, I'm going to switch to blue so I am guaranteed a blue line, a blue tangent line that will be parallel to that. So it is going to be right here, and it's going to skim right off, about right there. You are guaranteed that will happen. That your secant slope, which goes through the endpoints, will be parallel or equal to a tangent slope somewhere else. Okay, it also works the opposite way. You can start with a tangent slope and find a secant that would match that. That's the next drawing. Okay, here's a picture of a tangent slope. Tangent slope only touches one line. But I am guaranteed, because this is continuous and it's differentiable, I'm guaranteed that I could find endpoints that would be parallel to that. In fact, there are multiple of them. You can find at least one, but I could find a bunch. I could find a parallel endpoints that were between there and there. I could say these are my endpoints from here to here. I could make that my A and B, and I'd be guaranteed it would be parallel. I could do it from here to here. I could make that my A and that my B, and that would be parallel. Could I make, I'll make it in green. Could I make this my A, and could I make this my B? Why not? Clearly not. In fact, what kind of slope connects A to B? Well, it's not quite, but it's negative, right? Okay, and so that can't possibly be the right A and the B, but I'm guaranteed that I could find at least one or multiple other A's and B's that actually work. That is the essence of the mean value theorem. Okay, the guarantee that at some point the equality of the secant slope and the tangent slope exist. That equality exists somewhere. So let's actually solve it on a sample problem. First, the function x squared, does it satisfy the mean value theorem, the hypothesis requirements? The hypothesis is what is required. Does x squared satisfy that? So let's see, what do I need to have? I need to have continuity, I need to have endpoints, and I need to have differentiability. So I have all three. So I kind of like a checklist in my mind that I've got continuity, I have endpoints, and I have differentiability. And since all three are true, this satisfies the hypothesis or the requirements, which means now I should be able to solve the derivative equal to the average rate of change. So I'll set this up. I want to do the derivative equal to the average rate of change. All right, well, what's the derivative? 2x. What's the average rate of change? F of what? F of 2 minus f of 0. Those are my endpoints, are 0, 2 over 2 minus 0. So I should be able to solve this. I'm guaranteed that there should be a solution. So now I heard some of you say 4. So yes, f of 2 is 4 minus 0 over 2 minus 0. So that's solvable. So what does that turn out that x turns out to be? Yep. So x being 1 means it's happening at 1. 1 is the position, and you can see it's drawn in red on there. 1 is the position where the tangent line is parallel to the secant slope that connects the endpoints. So once it's satisfied the hypothesis, you're guaranteed that this is going to happen someplace. Let's try another one. Make sure that this satisfies the hypothesis on the MVT. All right, so I want to check, is this continuous? Do I have endpoints? Do I have differentiability? So kind of walk myself through that. Is this continuous? And the answer is yes. Do I have endpoints? What are my endpoints given? Negative 1 and 1, so yes. Is this differentiable?
Yes.
You sure? You sure? Check the graph.
It's not, because it was like that.
Okay. That's the graph. It's both sides of a square root, because a square root can be plus and minus. And so it's both sides. So what do I have? It's happening there at the origin. Yes, and so I don't have differentiability, which all that means is that the mean value theorem doesn't guarantee me diddly squat about this, okay? I do not have a guarantee, okay? I have guaranteed nothing.
Can you go back up one?
Mhm.
All right, cool, thank you.
All right, next one. Okay, so let's just make sure that we're good on this one. So they might sneak one of those in on your homework, right? So you just want to make sure you don't just blindly jump into the problem without making sure that it satisfies all three of the requirements. So this is a cubic. What do you know about cubics? They're continuous. Okay, do I have endpoints? I sure do. And do you know that cubics are differentiable? Yep, no corners in a cubic or cusps or anything. So I know that it's satisfied. So then the mean value theorem guarantees for me that the derivative must be equal to the average rate of change at least once. Maybe more than once, but at least once it will be. All right, so then I find my derivative, 3x squared minus 4, and I find my average rate of change, which will be f of 2 minus f of negative 2 over 2 minus negative 2. So 3x squared minus 4 equals, all right, so I need to know what f of 2 is. When you drop 2 into that equation, what do you get? I do. What if I drop negative 2 into that equation? I also get 0 over 4. Okay, what is 0 over 4? Okay, so I can cross multiply if you want. If you're not super comfortable, you can do it, make it like that. I love to do that with algebra. But that just tells me that 3x squared minus 4 must be equal to 0. So then x squared must be equal to 4/3, which means that x is equal to both the plus and minus square root of 4/3. And so this can be satisfied twice. That means there's two tangents that are parallel, bless you, to the secant slope. The secant slope you would draw, and there are two tangents in two different places that are also parallel to that. Okay, so you're guaranteed one, but you might get some bonus that show up. Yeah, Nico.
Do you have to plug that back in with the y?
Usually they're just asking you for the value of c, which would be an x value where that's happening. Okay, so somewhere in that interval, yeah.
Like, it's simple like a test or something, do you have to explain, like, there's gonna be like this, like, many, like, connections on the secant or the tangent or something?
So sometimes they might ask the question, how many times is the mean value theorem satisfied? Okay, so then you wouldn't tell them plus or minus rad 4 over 3, you would say 2.
Oh, but you're not gonna ever have to write it out.
Right, yeah. Okay, last one. A car begins and ends at rest. Okay, it starts, then it comes, and then it ends at rest too. During 8 seconds, it covers 352 meters. What does the MVT guarantee, and what does the IVT guarantee about this particular situation? All right, well, let's kind of think about our things here. Is the movement of the car continuous? In real life, yes. Okay, we're not jumping into hyperspace. We're not, using some portal to get from place to place. In real life, our travel is continuous. Okay, does my experience have endpoints? What are the endpoints? 0 and 8. Okay, yeah. Will this be differentiable? Again, yes, in real life, we're not bending time or anything here, so the travel is going to be differentiable. All right, so what does the mean value guarantee about this situation? It guarantees me that the derivative is equal to the average rate of change. Now, we don't have an equation, but you do know something about the derivative of the movement of a car. It's velocity, right? So this is the velocity is equal to, and then I can find the average rate of change, which would be f of 8 minus f of 0 over 8 minus 0. In other words, where is it when it at 8 seconds? 352. Where is it at f of 0? Nowhere, hasn't gone anywhere yet, over 8. So I can guarantee that my velocity is, at least one time in this situation, my velocity is what, 43? 43 watts? Okay. Meters per second. not squared. That would be acceleration by second. All right. So that means, does that mean the velocity is always 43 meters per second? No. It means that the velocity is at least once 43 meters per second. Okay, what would the IVT guarantee me about that then? If at least one time it was 43 meters per second, the IVT says that the endpoints, okay, where's the first endpoint? Okay, but the first endpoint is how much velocity do I have at the beginning? 0. And if 43 is an average, then what does that tell me about another velocity? Come on, if you've got 0 velocity, and at some point your average is 43, something has to be above 43 to make that average be 43. You can't, and so a police officer might say, sir, you have been speeding. If your average was 43 and you just covered this, the intermediate value theorem guarantees me that you went above 43 miles per hour in this particular zone. That's how they catch you with radar guns and little drones and all of that stuff, is they're checking your average over that. So the IVT guarantees you were going faster than 43 as well. All right, see you Friday.